Welcome. Today we are going to discuss chemical reactions, which are covered in sections 11.1 and 11.2 of your textbook. So just a general review, chemical changes occur when the chemical properties of matter change. So some classic examples of chemical changes are burning and rusting. I would like to point out that changes like boiling and melting are actually not chemical changes. Those are what we consider to be physical changes, because if you think about it, if you had ice, which is solid water, and you melt it, then it's now just liquid water, but it's still chemically H2O, and you could freeze it and turn it right back into ice. If you were to boil water, it goes from liquid water into water vapor, which you could recondense, and it's still H2O. Whereas if you burn something like a piece of paper, it's going to turn into ashes, which are a totally different chemical makeup than the paper that you started with. It takes some practice as you are starting to learn chemistry to truly identify whether something is chemical or physical or not. One rule of thumb to use is if you can reverse a process or a change, then usually it's just a physical change. Whereas if it's irreversible, then it's probably chemical change. Some other clues that you can look for that help you decide if a chemical reaction has occurred. We discussed these early on in the semester, but just a refresher. If there's bubbling or a production of a gas, like when you mix baking soda and vinegar together, then that's a clue that you had a chemical reaction. Now be careful though, because boiling water will still bubble, but it's not changing the chemical makeup of the substance. A color change, like leaves in the fall, the leaves are actually dying, and that's why they are changing colors between their different pigments, the chlorophylls, the xanthophylls, and all of that. Bananas, when you first pick or buy a banana, it's green and it's kind of gritty. It doesn't have a sweet texture or flavor to it, but as it sits on your countertop or in the grocery store, it will start to turn yellow and then eventually brown. And as the color changes, so does the sugar content, which makes it sweeter. Production of light and heat, like the flame test that we did, or when something is caught on fire. Forming a precipitate, which remember, precipitate's kind of a long word, so we generally abbreviate it as PPT. A precipitate is when a solid forms when you mix two liquids. Now, it is the more items that you can check off of this list when you have something happen. Like if you mix two chemicals and you have a color change and a precipitate form, then it's probably going to be a chemical reaction. The more boxes that you can check off of this list, the more likely it is that what you're working with is a chemical reaction. All right, some other general information. In chemical equations, we write the reactants on the left side. Reactants are the chemicals that you start with. Then we use this arrow. That is called the yields arrow. You do not use an equals sign in chemistry because they don't equal. It's turning into products, which is the stuff that you make. So if you had a skeletal equation like Na for sodium reacts with chlorine, yields sodium chloride, the sodium and chlorine over here on the left would be considered your reactants, and the sodium chloride would be the product because it's on the right side of the equation. All right, some other common symbols that you might come across as you are writing and balancing equations. The plus sign is used to separate chemicals and to show that they are reacting with one another, or that they're being produced and they're separate. The arrow stands for yields or reacts to form. When you see a double arrow like this, that indicates that a reaction is reversible, so it can go one direction and then turn around and turn back into what you originally started with. If you see this little triangle over the yields arrow, that means that heat is added, so you maybe put this over a flame or on a hot plate to help the reaction move along. Phase labels. All right, so like when you're cooking, it's really important that you get the right ingredient. For example, sometimes you need butter in its solid stick form, and the recipe will say a stick of butter. Whereas in other recipes, you need the melted butter, so you would have to put it in the microwave or put it on the stove, and it can really change your product that you're making by what type of butter or what phase you selected. So the same is true in chemistry. If something is a solid, you'll put an S in parentheses after it to show that it's solid. If it's a liquid, we put a cursive lowercase l in parentheses. And if it's a gas, we put a lowercase g in parentheses. For elements, when you're trying to decide what their phase label is, a lot of the periodic tables, like the one in my classroom above my whiteboard, are color-coded, and the different colors will tell you if something is a solid, liquid, or gas. Another rule of thumb, most metals are solids at room temperature, except for, remember, mercury is liquid. It's the only liquid metal. The non-metals are generally gases, but some of them can be solids. Bromine is the only liquid non-metal. There actually is a fourth phase that I would like to introduce to you. There's a fourth phase label that's AQ in parentheses. That stands for aqueous. The Spanish word aqua means water. So aqueous is what we use for something that has been dissolved in water. Sometimes these are called solutions. So if something is ever described as a solution, then you should put aqueous as the phase label. Acids are always aqueous. Think about like when you make Kool-Aid at home, you have to take Kool-Aid powder and sugar and dissolve them in water. So Kool-Aid is an aqueous solution. One thing that can be a little bit confusing is that water itself is never aqueous, because aqueous means something dissolved in water. So I never want to see you put aqueous as a phase label after water. Instead, you should put H2O liquid, unless of course the problem says that you're working with ice. Ice would be solid water, so you'd put H2O with an S in parentheses after it. If the problem says that you're working with steam or water vapor, you would put H2O with a G in parentheses after to show that it's gaseous water. All right, the next big item that we have to review is the law of conservation of mass. The law of conservation of mass says that under ordinary conditions, mass can neither be created nor destroyed. So you have to start and end with the same total amount of atoms and stuff that you began with. So as we go to write equations, chemical equations are kind of like recipes. Just because you throw out a random recipe doesn't mean that it's actually going to work out or that it's proper. Same with chemical equations. In order for an equation to be valid or correct, there are two main criteria that it must meet. First of all the formulas that you write have to be correct. One of the main areas where I see people go wrong here is that they forget the diatomic elements in their pure state. Remember, diatomic elements are the elements that have to come in pairs. Bromine, you'll never find a single atom of bromine by itself. Bromine will come as Br2, and it has a phase label of liquid because it's liquid in its pure state. Iodine comes as a pair. Nitrogen is N2, chlorine is Cl2, hydrogen is H2, oxygen is O2, and fluorine is F2. You kind of just have to commit those elements to your memory so that you know. I do want to throw out there that this only applies in their pure state. So if the equation or the word equation says that you have bromine or oxygen, then you would write this. If this is combined with any other element, like if it's hydrobromic acid or sodium bromide, then you don't put a 2 with it. All right, the second criteria after you get all of your formulas correct is that the equation has to be balanced, and it has to be balanced in order to obey the law of conservation of matter, because if it's unbalanced, then it looks like you have created or destroyed matter. Now, as you go to balance equations, there are certain things that you can do and certain things that you cannot. In order to balance an equation, you can change coefficients, but you cannot change subscripts on items. So an example that I gave here is this 3H2O, 3 waters. A subscript would be this maroon number right here. You are not allowed to change that. Why are we not allowed to change that? Because let's say we took that out of there and we just had H HO? Or what about if we had like an H3O? That's not water. That's something completely different. You're not allowed to do that. You are, however, allowed to put these coefficients out here. And if you put a coefficient out there, that multiplies across the entire molecule. So when I wrote a 3 out there, now that means I have 3 times 2 hydrogens. I've got 6 total hydrogens. I also have 3 times the 1 oxygen, so there's 3 total oxygens. Okay, so let's try to turn a word equation into a balanced chemical equation. So our word equation says hydrogen reacts with oxygen to form water vapor. All right, hydrogen, the symbol for hydrogen is H. Then we ask ourselves, is hydrogen a diatomic element? Well, it's on our list, so we can't just put hydrogen, we have to put H2. The phase label for hydrogen, when you look it up on the periodic table, is a gas, so I'm going to put a G in parentheses. Reacts with, so I'm going to put a plus sign. Oxygen. Oxygen is O, but oxygen is one of those diatomic elements, so I have to put a subscript of 2 there. It's also a gas. To form. So to form, I put my yields arrow here. And water vapor. Water is H2O. Since they called it a vapor, I'm going to put a gas on it. Now, how do we balance this? This is the way that I would like for you to begin. As you get more used to this and you practice this more, you might not have to do all of this scratch work. You might be able to do some of this in your head, but I would not try to skip there right now. So the law of conservation of matter says the total number of atoms of each element you start with has to equal the total number that you end with. So here is what I recommend. I recommend that you draw a border line under the yields arrow. That way you can keep your reactants separate from your products. And then you list what elements you have. We have hydrogen and oxygen. You are always going to have the same elements on the right side because you're not going to turn them into different elements. All right, then we count up. We have 2 hydrogens. And we have 2 oxygens on the left side. On the right side, I have 2 hydrogens, but only 1 oxygen. Right now, this looks like it is not balanced because it looks like you started with 2 oxygens and you ended with 1. How do we fix this? Well, we've got some ideas that you could use. You could put 2 down here to try to get 2 oxygens. But if we go back to our rules here, it said that we could not change subscripts, so that's a bad idea. By the way, H2O2 is hydrogen peroxide. That's a completely different substance than water, which is why you can't do that. So the only option that I do have is to put a coefficient of 2 here. So now I've got 2 times 1, which is 2 oxygens. However, now I have 2 times 2, which is 4 hydrogens. Balancing equations is kind of like cleaning your room. It's going to look worse before it looks better. So now my oxygens balance, but my hydrogens don't. I've got 4 hydrogens on the right and only 2 on the left. So I'm going to have to add a coefficient of 2 in front of this hydrogen, and 2 times 2 gives me 4. Now my equation is balanced. You are really going to learn this just by trial and error and practicing. I would highly encourage you to show your scratch work here while you're trying to balance it, and do this in pencil because you're going to make mistakes and need to change things. All right, moving on to section 11.2 in your textbook. In section 11.2, 5 basic types of reactions are discussed. The 5 types are combination, decomposition, single replacement, double replacement, and combustion. So I have now given you a general form for each of these. In a combination reaction, you take A plus B, so 2 substances, and react them together to form 1 new substance. So your telltale sign that this is combination is on the right side of the equation, you're only going to have 1 substance. Decomposition is the opposite. You start with 1 substance and you break it down into A plus B. Single replacement, sometimes single replacement is called a substitution reaction. So you take an element and you react it with a compound, and this element will take the place of one of the other elements. So like A has substituted in for B. Now B is by itself and A and C are linked together. I do want to tell you that you have to substitute a metal with another metal or a non-metal with another non-metal. You're not free to just make any substitution or replacement that you want. Kind of common sense. I mean, like if you're playing football and your quarterback is injured and goes out, you usually don't go get a defensive lineman to come in and take their place. You're going to get a backup quarterback or someone of similar skill to take their place. Double replacement is very similar, but this time I had A, B reacting with C, D, and the A and the C swap places. So your cations switch basically, because remember cations are the first ion in the compound. All right, and then the last type is combustion. When you hear combustion, you usually think of something exploding probably, or fire. That's essentially what's going on here. So you have some substance, which we'll call X, and it reacts with oxygen because oxygen is necessary for a fire. Now remember, oxygen is a Brinkelhoff, so it's O2 and it's a gas. And combustion will always make the same two products, CO2 gas and H2O gas, so carbon dioxide gas and water vapor. It's water vapor because there's so much energy released from this that the water is given off as steam. All right, let's try practicing these a bit. So we are supposed to balance and classify. And I also left some phase labels blank for us to practice. So in this case, I have Cu with no phase label. That's copper. So I look copper up on the periodic table, and copper is in a solid form when it's by itself. Reacting with AgBr, I went on ahead and told you that's aqueous because you're beginning chemistry students, and I would not expect you to know that. Those of you taking chemistry 2 next semester, we will work on phase labels for compounds. Now I have Ag, which is silver. It's by itself, so I looked it up on the periodic table. Has a phase label of solid, and it's going to make CuBr2 aqueous as the other product. All right, so let's balance this thing. So I'm going to draw my border line, and I'm going to list. I have copper, I have silver, and I have bromine. Then I'm going to write those exact same elements in the same order on the right side so that I can compare and keep track. So on the left side, I had 1 copper and 1 silver, 1 bromine. On the right side, I had 1 copper. It's only 1 copper. The 2 is right next to the bromine, so it only applies to the bromine. And then there is 1 silver. All right, so this is not balanced right now. I have 2 bromines on the right and 1 on the left. In order to get 2 bromines on the left, I'm going to have to put a coefficient of 2 out here. But by doing that, I also changed the number of silvers to a 2. All right, so now my bromines are balanced, but my silvers are not. I have 2 silvers on the left, only 1 on the right. So I am going to need to put a coefficient of 2 there, and it balances. Now, to try to figure out what type of a reaction this is, I usually say go through and throw out the options that you know it cannot be. So the easiest one to throw out is combustion, because if this is combustion, you will have to make CO2 and water as your products. We're not making CO2 and water, so we can cross that out. Next, I say check if it's a combination. If it's a combination, you only have 1 product on the right side. We have more than 1 product, so that won't work. Decomposition is similar because you would need to start with 1 item. We are not starting with only 1 item on the left, so it can't be that. Now we're down to a single replacement and a double replacement. So what you're looking for, if it's a single replacement, you have a pure element reacting with the compound. If it's a double replacement, you have 2 compounds reacting. Right now I have the pure element copper reacting with the compound of silver bromide, so this is a single replacement reaction. All right, let's try the next reaction. So the next reaction, I have AlCl3 solid. Put a yields arrow. The little triangle tells me that this is heated up. Then I have that turns into aluminum. I look on my periodic table and the phase level for aluminum is solid plus chlorine gas. Now I put Cl2 because chlorine is one of those diatomic elements that comes in pairs. All right, let's just go ahead and classify this right now. So we definitely don't have combustion here because we're not making CO2 and H2O. If this is a combination reaction, I have to have one product. I don't have one product, but I do have only one reactant, which makes this a decomposition reaction. All right, now let's balance it. So we're gonna draw our border line here. Then we're gonna list what we've got. We've got aluminum and chlorine on the right side. I have 1 aluminum and 3 chlorines on the left, 1 aluminum, 2 chlorines on the right. Definitely not balanced. Now we've kind of got a little bit of a problem because there's no whole number that I could write in front of chlorine to turn it into a 3. So sometimes we have to use some math skills, and instead of turning it directly into the number, we have to find a least common multiple. So 2 and 3 are both multiples of 6. So let's try to get 6 chlorines on each side. So if I put a 3 here, that's gonna give me 3 times 2 or 6 aluminums. If I put a 2 here, 2 times 3 is 6 chlorines. So now my chlorines balance. But I changed my number of aluminums. Now I have 2 times 1, 2 aluminums. So in order to get the aluminums to balance, I need to put a coefficient of 2 here, and life balances. Like I said, this will get easier the more that you practice it. All right, our next reaction that we're gonna work with. Let me change my color here. So we have CH4 gas reacting with oxygen. Oxygen is a gas to make CO2 gas and water vapor. All right, it's looking good. We got a CO2 and a water vapor and we reacted with oxygen. So this is a combustion reaction. All right, let's balance it. We draw our border line. We have carbon, hydrogen, and oxygen. Carbon, hydrogen, and oxygen on the right side. We count them up. We've got 1 carbon, 4 hydrogens, 2 oxygens. On the left side, we have 1 carbon, 2 hydrogens. Now, oxygen gets a little tricky here because we've got 2 oxygens here, but we also have another oxygen there. So 2 plus 1 tells me that I have 3 oxygens. All right, this can be a little tricky when you have one element in more than one place on the same side of the reaction. So what I suggest is, because oxygen is a little difficult to deal with, that we save it till last. And usually it's gonna work itself out in a combustion reaction. So let's look here. Our carbons are balanced. Our hydrogens are not. We have 4 hydrogens on the left, only 2 on the right. So I'm gonna put a coefficient of 2 here. 2 times 2 gives me 4. Now, I have changed the number of oxygens here to 2, but I can't forget that I also have these 2, so 2 plus 2 gives me 4. All right, 4 oxygens on the right, 2 on the left. I can put a 2 here, and 2 times 2 is 4, and it's balanced. All right, our final reaction for this sample set. Potassium reacts with chlorine to produce solid potassium chloride. All right, potassium is K. Potassium is not a Brinkelhoff, so we do not have to put a subscript of 2. Brinkelhoff is an acronym for those diatomic elements, by the way, if I haven't mentioned that. So it's not a diatomic. I look at the periodic table, and according to the color coding, it is a solid. It reacts with chlorine, so I'm going to put Cl. Chlorine is a diatomic Brinkelhoff element, so I have to put a 2 subscript. When I look it up on the periodic table, it's a gas phase. And to produce, I put my yields arrow. Now, potassium chloride, the fact that it has "ide" tells me it's ionic. So I've got to go back and use those rules we learned last chapter and figure out what the formula is for potassium chloride. So potassium ion is K plus 1. Chloride is Cl minus 1. So when I crisscross those, I get K1, Cl1. So KCl. And they told me in the problem that it's a solid, so I'm going to put solid. All right, that's the correct skeletal equation. I've got my formulas correct, but now let's balance it. So I have K and Cl, K and Cl. I have 1 potassium, 2 chlorines on the left, 1 potassium, 1 chlorine on the right. So to get 2 chlorines on the right side, I've got to put a coefficient of 2 out here. 2 times 1 is 2, but I also have changed the potassiums to 2. So now to get the potassiums to balance, I'm going to have to put a 2 on the left side. All right, this is balanced, but we have not yet decided what type of a reaction this is. So let's go through our list. Is this combustion? If it was combustion, we would have to make CO2 and water vapor. We didn't make CO2 and water vapor, so that can't be it. Is it a combination reaction? Because a combination takes 2 things and turns them into 1. That's exactly what we've got going on right here. We had potassium plus chlorine making 1 final product of KCl. So this is, in fact, a combination reaction. I hope this overview and set of sample problems has helped you to better understand how to write and balance equations. My biggest suggestions and reminders to you: do not forget your Brinkelhoffs. Don't forget the diatomic elements, because if you mess that up, it'll be really hard to balance. The second thing, when you go to balance, you are only allowed to change coefficients, not subscripts. All right, happy practicing.